Okay, we're going to look at some harder SUVAT examples now. And a lot of these are going to be where we've got connections between two sets of figures. So the first example, I'm going to read what the question says on the sheet that you're going to have. It says, telegraph poles 40 metres apart stand alongside a straight railway line. The time is taken for locomotives to pass the first two gaps between the three consecutive poles of 2.5 seconds and 2.3 seconds respectively. Assume that the acceleration of the train is constant, calculate that acceleration and the speed past the first post. Now, I've labelled the posts A, B and C to help me out, because what you'll find is we've only really given for each stage of the motion two facts, and as I said before, a SUVAT equation links 4 of the 5 letters. So I can only solve it if I know 3 things. So I can't solve for one thing here, but we're going to have simultaneous equations in this case. So I need to look separately at the SUVAT from A to B, B to C, or even A to C. And there's going to be links between them. It's the same acceleration, there's an alternative I can do, and I'll talk about with one of the other examples. So I'm going to do A to B, do my SUVAT setup, S equals 40, it's all that. U, we're going to call it U because that's what I'm after. V is the speed at B now. We'll come to that in a moment. A is constant, we'll call it A, and T is 2.5. I could consider B to C and have its distance displacement is 40, its initial velocity is actually whatever that value of V is there. So as it goes through B, what is the V value for the first part of the motion becomes U for the second part of the motion, same acceleration and the time 2.5. What I'm actually going to do though is the whole lot from A to C, because it's going through A, it's still got the same value of U. So I know that in this case here, S equals 80, U equals U, V is its velocity at C, not interested in that or that, A equals A, and T, the total time, is 4.8 seconds. So what I've got now, I can do 2 equations with 2 unknowns, U and A, and I'm going to solve them. So it's, in each case, it's the one without V, so I'm going to be using S equals UT plus a half AT squared, and so for this one, I've got 40 equals 2.5U or 5U over 2, and then plus a half a t squared. Oh gosh, 5 over 2, 25 over 4, half 25 a over 8. And in this case here, 80 equals 4.8, 48 over 10, 24 over 5, 24 u over 5, and then plus whatever the mess is of 4.8 squared, and then halve that. You know what? It's button pressing time. Let's have a look now. I could work it out, but it was late on a Monday evening. 288 over 25, so 288a over 25. So I can turn these into simultaneous equations and solve them. I can times that by 8, for example, to get 320 equals 20u plus 25a. I could actually divide by 5 to make them a bit smaller. I might do later on, we'll see. Times these by 25 is going to be 2000 equals 5 times 24, 120u, and then plus 288a. I'm almost there because I can times that by 6 to get 120u. 320 times 6, being lazy like 1920, equals 120u, and then 6 times that plus 150a. And if I minus them like this, I've got 138a equals just 80. So 80 divided by 138 equals 40 over 69, 0.57, 0.58 meters per second squared. I can stick that into either of these. I'm going to use my previous answer and can stick into this one, times by 25 equals that, 320 minus my answer equals that, divided by 20 equals, and I've got 15.3 metres per second. U equals 15.3 metres per second. Now, obviously with your fancy newer calculators, you can just put the two equations in simultaneously and it'll churn out the answers for you. But it's nice to actually show where they come from. But our method, as I say, notice I use my diagram, I label what I'm doing, A to B, B to C if I was going to use it, then A to C, and I've used that in each case because I need the value of U and use the initial speed for both A to B and A to C, and use the information I've got to get its displacement, its time, set up my simultaneous equations, press buttons, and there's my answer. Now, second example, I've already begun to do the solution to it. We'll read it. It says a cyclist travels from A to C, a distance of 240 metres. He passes A at 12 metres per second, maintains his speed for as long as he can, and then brakes, so he comes to a stop at C. If the maximum deceleration you can achieve when braking is 3 metres per second squared, find the time and distance covered whilst braking. So I need that distance there as well. And then the least time in which you can get from A to C. So let's have a look at this then. And I've done it as a velocity time graph. Why have I done this is because I think that anytime you've got one particle with two different stages of motion, two different constant accelerations, or even three of them, velocity time is the way to go. Your typical question like this is cars leaving from between traffic lights, accelerating constant velocity and decelerating. And once you've got multiple stages of motion for one thing, I'd be looking to put it into my velocity time. I can see things clearly now. So for example, I know that I'm using the gradient to find what T2 is, the time that it decelerates. All the gradient is 3 is 12 over T2. So I know that the gradient acceleration 3 is 12 divided by T2, which means that T2 is 12 over 3, which is 4 seconds. And if that's 4, I can work out the distance that it covers there. So the distance that it covers in that time, it's a triangle, a half times 12 times 4, which is 24 metres. What that means is my rectangle is 216 metres. So now that 12 times T1, area of the rectangle, is 240 in total. I'll take that off the 240 at 216 metres. So T1 is whatever 216 divided by 12 is. I think it's 18, but I'll just check. 240, yeah, it's 20 minus 2, which is 18 seconds. So the total time then, because it wants the least time you want to get from A to C, T1 add T2, is simply 18 add 4, 22 seconds. And I haven't used a SUVAT as such, but I sort of have. I'm using acceleration is change in velocity over time. I'm using displacement is area under the graph, but I'm doing it in bits. Okay, so in that case there, I can just do bit by bit. Everything seems to match what I've got there. I'm fairly happy with all my figures, but velocity time is the way to go for one particle with multiple stages of acceleration. Last example, these ones, gives me velocity time, but it's for two particles, two trains. A and B moving on straight horizontal tracks, run alongside each other. A starts off slower, but it's got a steeper line, so it's accelerating more. B starts off faster, but it's a gradual one. After 8 seconds, they're both travelling with the same velocity. Now, it doesn't mean they're at the same point, because obviously A started off going slower, but it's going to catch up and then go past at some stage or other. So we want to find the distance between them at t is equal to 8 and which one's gone further. So what I can do, I can say for each one individually, I can just work out the area under the graph. It's the average of the parallel side, so it's a half 1 plus 5.8. We're using the speed time equation is really rather than SUVAT because I've got a velocity time graph. So 6.8 times by 4, 28, 27.2. Displacement of B, in the same way, is its area, 5 to 5.8, so it's a half, 5 plus 5.8, times by the 8 seconds in between, so it's 10.8 times 4, which is 43.2 metres. Displacement between them, SB minus SA, is 1 minus the other, 60 metres, with B ahead. And that was worth not as many marks as the second part, so 3 marks, and the second part's worth 8 marks. I might need my second board over there in a moment. So it says it wants the time when A is 9 metres ahead of B. So I'm going to do my SUVAT, in this case, separately for A and for B. So whatever you want to do for S, I'm going to call the displacement that B travels S, and this one then is an S at 9. So there's a link between them basically. I haven't got enough information here. I don't know what the acceleration is. All I know is that for this one, U is equal to 1. For this one, U is equal to 5. V, not interested in. V, not interested in. It's the same acceleration. No, it's not. It's a different acceleration. Because all I'm going to do is I'm going to call it A and A. So yet again, I'm not interested in A either. But T is the same time. So what I've got here is not a massive amount on the time. So I know that there's a link between them. I'm going to use the fact that they are different accelerations and different velocities. I'm trying to think about when I'm doing this, 9 metres ahead. It's quite hard to see in this case exactly what I'm doing because I'm being a bit silly really, aren't I? I can use the information that's there to work out the acceleration in each case. I've got enough information there to know that, for example, A goes 4 metres per second increase over 8 seconds, so its acceleration is 4 over 8, 0.5. I know that B goes from 5 to 5.8, 0.8 metres per second in 8 seconds, so its acceleration is 0.1. I'm panicking then a little bit, to be honest. So in that case, it's still the one without V, so it's S equals UT plus a half AT squared. That's more like it now. And I'm just going to say that for A, S at 9 equals 1T, and then a half times A, which is a quarter T squared. And for this one, S equals UT, which is 5T, and then plus half of that, 0.05 T squared. And I can substitute that into that, eliminate S in my equation, and say that 5T plus 0.05 T squared plus 9 equals T plus 0.25 T squared. Move it all across, get my quadratic, and then look to solve it to find the time, and that's what the question is. So that taken away from that becomes 0.2 T squared. T minus 5 of them is minus 4 of them, and then minus 9 equals 0. 0.2 is a fifth, so I've got T squared minus 20T minus 45. And I think it's going to factorise T. Is it going to factorise? Not quite. So I'm going to do complete the square, T minus 10 all squared minus 100 and that, so it equals 145. T equals 10 plus or minus. Now 10 minus will be a negative value, so it's 10 plus root 145, so just over 22 seconds, so 22.0 something. So 10 plus root 145 equals that, 22.04, so 22 or 22.0 seconds there. So at that time, it's when A's gone and overtaken B, and it's gone 9 metres ahead. So it's simultaneous equations. I had a panic because they'd only have to give me one value, U in each case, but they had enough information there for me to work out A, didn't need V, but there's a link between them. So when there's two particles, they're going to be linked by same time, slightly different distance, or if one catches the other one up, it might be the same distance, but one set off at a different time, so there'll be a link, one set off 2 seconds after the other. So there'll be a link between the two things in that way there. So in that case, we're looking at velocity time where appropriate, using SUVAT to set up simultaneous equations where you can.